Hey there, Seahawks. It's Miss Adams, and in this video, we're going to talk about experiments and experimental design. All right, an observational study is when researchers do not impose a treatment on the experimental units. They simply observe. Two types of studies are retrospective and prospective studies. In a retrospective study, we select the experimental units, then ask about previous behaviors and conditions. All right. And then prospective study is we identify the experimental units in advance and then collect data as events unfold. So we follow them. All right. Type of study. So our first example, researchers looked at records of tenants at an apartment building over the past 5 years to determine if the landlord had a preference in the race of his tenants. Right, that would be an example of a retrospective. Okay, so we're looking back 5 years. Example 2, a local school identifies 50 kindergartners who are considered at-risk students and tracks their progress through high school graduation to see if the programs already in place in the district help these students. All right, so we identified them in kindergarten and we stuck with them. We followed them through high school graduation. So that would be a prospective study. All right, in experiments, we impose a treatment. We manipulate factors and levels to create treatments. We randomly assign subjects to those treatments, and we compare the responses of the subject groups across treatment levels. Experimental units are individuals on which the experiment is done. All right, so this could be animals, cars, plants, whatever. Subjects is when I have human experimental units. The factor is the Factor is the explanatory variable or variables. Levels controlled by the experimenter. The level is the specific value a factor can take, and the treatments are a combination of levels of each factor, the specific thing being done to each group of experimental units. All right, our first example where we're going to do an experiment. You work at a botanical company, and with your team, you have developed a new type of potting soil, specifically designed to improve the growth and development of roses. An experiment needs to be designed to show that your soil works well compared to the leading competitors. How can you design a good random experiment? All right, so measuring the effects of 2 fertilizers and 3 water amounts on a plant growth, we could look at that. So my factors would be fertilizer and water, and my levels would be the fertilizer A and B, and then water different amounts, so like 100 milliliters, 200 milliliters, 300 milliliters. And my response variable would be whatever it is I'm going to measure. Okay, so maybe I'm measuring height of the plant in inches, width of the plant in centimeters, number of buds on the plant, number of leaves, color of the plant, etc. All right, principles of experimental design. So control, randomization, and replication. We need to have those. We want to control as many aspects of the experiment as possible. We want to anticipate and reduce the effects of lurking variables, and we want to use a control group. Randomization, we want to randomly assign experimental units to treatment groups. All right, so assign each experimental unit in the sample a number, use the table of random digits to assign experimental units as evenly as possible to treatments, or put all the experimental units in a bag, shake it, and pick to assign treatments. Replication, repeat the experiment on many different experimental units. Repeat the experiment on many different samples from the same population. Replication helps show validity of our results. All right, so if you replicate it and you see the same or similar results, then we can say it's valid. All right, the control group are experimental units assigned to the baseline treatment. This may include no treatment at all, the old or default treatment, or a placebo. A placebo should be used if an experiment has subjects, so if we're working with people, a treatment known to have no effect, or it's a dummy treatment. A lot of times it's a sugar pill. The placebo effect is the tendency of human subjects to show a response even when administered a placebo. All right, so even when they get a sugar pill, they say that their pain has decreased. All right, so this is their mind has convinced their body that they are feeling better, and their body shows a response. All right, completely randomized design. Randomly and evenly assign experimental units to treatments. So our first example, we'll have 36 rose plants. We're testing 3 different types of soil, and we're measuring the size and health of those plants. All right, so we're going to start with 36 rose plants, and we're going to randomly assign them to the different soils. So we have 3 different types of soil. I'm going to call it A, B, and C. So if I have 36 and I divide that by 3, that means it's going to be 12 each. Again, I'm randomly assigning them. And then I'm going to compare the size and the health of those plants. I do have to also specify how did I do that random assignment. All right, so my random assignment, I put the rose plants in a bag, shake the bag. The first 12 selected get soil A, the next 12 get soil B, the rest get soil C. All right, there's multiple ways you could have written that out. All right, but that is what random assignment would look like. Blindness. Single blind is when one group, the experimental units, or the researcher recording the results, do not know the experimental unit is getting which treatment, right? Double blind is when both of the groups, the experimental units and the researchers recording the results, do not know which experimental unit is getting which treatment. Blinding can help to reduce bias when it's possible. All right. Your turn 1. I want to test out a new plant food. So I take 20 plants and give half the new plant food and half no food at all. All of the plants get some amount of water and sunlight each day. After 30 days, I measure the height that the plant has grown and also how many flowers it has on it. All right, so my individuals will be the 20 plants. My factors are food. The levels are the new food or no food. And the treatments are new food or no food. My response variable, what I'm measuring, is the height and number of flowers on the plant. All right, so I'm starting with 20 plants. I'm going to randomly assign 10 to get the new food and 10 to get no food. All right, then I'm going to compare the height and number of flowers. Again, I have to say how I'm using that random assignment. So put 20 plants in a bag, shake the bag, the first 10 get the new food, the rest get no food. All right, your turn number 2. High cholesterol levels in people can be reduced by exercise or by drug treatment. A pharmaceutical company developed a new cholesterol-reducing drug. Researchers would like to compare the effects of this new drug with the currently used and accepted drug. 100 volunteers who have a high history of high cholesterol and who are currently not on any medication will be recruited to participate. What are the treatments and what are the subjects or individuals? Well, the treatments are the new drug and the current drug, and the subjects or individuals are 100 volunteers with high cholesterol. The response variable is the cholesterol level. Would a placebo group be appropriate or necessary? Why or why not? So yes, we're using human subjects, so we would want to include a placebo group. All right, design the experiment. So I have 100 volunteers. I would randomly assign some of them to each of these groups. So I'm going to do 33 to the new drug, 33 to the current drug, and 34 to the placebo. I can't do an even amount, so one group's going to have one more than the rest. I'm going to compare my cholesterol levels, and again, I randomly assigned, after I had my 100 volunteers, I randomly assigned them to their treatment groups. So I have to say how I went about that. So assign all 100 volunteers a number from 1 to 100. Use a random number generator to select 33 numbers from 1 to 100 without repeats to get the new drug. The next 33 unique numbers go to the current drug, and the rest go to the placebo. All right, so again, you could do the shake the bag method, or you could put assign them numbers and use a table of random digits or a random number generator, something along those lines for your random assignment. All right, 2-factor design. 36 rose plants testing 3 different types of soil and 2 amounts of water, none or once a day. Still measuring size and health of the plant. Okay, so this is similar to what we had before. So I'm starting with 36 rose plants. I have 3 different types of soil A, B, and C. I'm randomly assigning them to which soil they get. Then I'm also going to have the factor of water. So some are going to get no water, some are going to get water once a day. So out of the 12 in soil A, 6 get no water, 6 get water once a day. I'm going to repeat that for soil B and soil C. And then I'm going to compare the size and health of the plants. All right, again, I am randomly assigning them to their soil groups. And then within each soil group, I'm randomly assigning them to the amount of water they're going to get. All right. Block design or blocking. A block is a group of similar experimental units that would have an effect on the results. So maybe gender, age, breed, etc. So block the roses we have used before based on type of rose. So Alba rose and a rock rose. All right, so for blocking, I'm starting with what I have. I have 36 rose plants. I'm going to block them by the type of rose. So I have Alba roses and rock roses. I don't know the number of roses I have in each of those, so I'm not going to put numbers with it because I don't know if it's even split or what. Then I'm going to assign them to their different soils, and then I'm going to compare the size and health of those plants. All right, I am randomly assigning after I've sorted them into their different blocks. Okay, I cannot randomly assign them to be an Alba rose or a rock rose. They either are an Alba rose or a rock rose, or they are not. All right, again, we want to say how we did that random assignment. So put all the Alba roses in a bag. Shake the bag. Pull out one at a time. The first one selected goes to soil A, the next soil B, then soil C. Repeat the ABC cycle until I have placed all the Alba roses. Repeat this process for the rock roses. And if you don't like the idea of drawing out the diagram, you can explain this whole process in paragraph form as well. All right, let's go back to the experiment on people with high cholesterol. We want to test the effect of a new drug and an old drug. We also thought a control group would be useful. There are 100 volunteers with high cholesterol that are currently not on meds that are available. So my individuals are the 100 volunteers with high cholesterol. My treatments are the new drug, the old drug, and a placebo. The placebo is going to act as a control group. My response variable is their cholesterol level. What are some lurking variables in this experiment? So maybe their exercise level, their diet, their genetics, their sex, their age. Maybe all of those things might have some impact on the results. Using the variables, create a block design for this experiment. All right, so I have 100 volunteers. I'm going to block them by exercise level. So I'm going to do low exercise, medium exercise, high exercise. And then within each exercise group, I'm going to assign them to either the new, old, or placebo drug. All right, and then within each block, I'm going to compare the cholesterol levels. So again, I'm not randomly assigning them to their exercise. Like I'm basing that off of what their current exercise levels are. Okay, so if they have very low exercise levels, then they go into that group. If they have medium exercise levels, they go into that group. All right, so put the names of each volunteer into a bucket based on their level of exercise. Shake the bucket. Pull out one at a time and assign new, old, or placebo until gone. Repeat for each bucket. Again, you want to try to make that random assignment as clear as possible so that somebody could replicate your experiment. All right, your turn number 4. Men and women respond differently to advertising. An experiment to compare the effectiveness of 3 TV commercials for the same product will want to look separately at the reactions of the different genders and assess their overall response to the ads. There are 70 people available for the experiment. What are some lurking variables in this experiment? All right, so gender was our lurking variable that we were going to take into account, and then because of that, we're going to block by that. So using this variable, create a block design experiment. So I have 70 people. I'm going to block them by men and women, and then I'm going to randomly assign them to the commercial that they get, and I'm going to compare their reactions. All right. I'm going to do that same process for women. Again, I am not randomly assigning them to be either men or women. I am randomly assigning them after they've been blocked by men or women. All right, and make sure that you explain the randomization process. A matched pairs design is usually only 2 treatments. Each experimental unit gets both treatments, and you randomize which treatment comes first or second, or which one goes on the left or the right, or the front or the back, or etc. Can also be where 2 subjects with equal characteristics are given different treatments and then compared. Okay, so we're going to do an example as a taste test of Coke versus Pepsi. So we're going to start with some experimental units, and we are going to break them up into treatment group 1, where they're going to have Coke first and Pepsi second. And then treatment group 2 is going to have Pepsi first and Coke second. And we're going to compare the results. All right, and make sure we are randomly assigning those. Okay, your turn 5. We want to test the effectiveness of 2 types of tires, call them A and B, on cars. We gather 50 different cars from our experiment. We will be measuring the amount of wear on the 2 types of tires. The cars will be driven normally for 3 months. How could we best design this experiment? So, what are the individuals and what is the response variable? So, 50 cars are our individuals. My response variable is the wear amount on the tires. What are the treatments? Tire A and tire B. All right, we're going to design this as a matched pair. So we're starting with 50 cars. We are going to randomly assign them to treatment 1 and treatment 2. So treatment 1 is going to get tire A on the left side, tire B on the right side. And treatment 2 is going to get tire A on the right side, tire B on the left side. All right. And I'm going to compare the amount of wear on the tires for both groups. Okay. And then I may compare treatment 1 and treatment 2. It just kind of depends on the variables. Can this experiment be a single or double blind? That would be a little bit silly. You could maybe make it a single blind where the researchers don't know until the end, but the cars, we don't need to blind them. All right, your turn 6. Go back to the car tire experiment. Suppose the cars were all different. So you have SUVs, sports cars, sedans, trucks, etc. How would you reduce a lurking variable of car size or type? All right, so we could use blocking. All right, so we have our vehicles. We could block them by type. So we'll do SUV, sedan, and truck. And then I could randomly assign them all of the SUVs to either treatment 1 or treatment 2, all of the sedans to treatment 1 or treatment 2, and same with the trucks. All right, and then compare the wear of the tires. I am randomly assigning them after they are blocked to their treatment groups. All right, the best experiments are usually randomized, double-blind, comparative, and placebo-controlled. Okay, however, you don't have to have all of those things, right? Randomization, replication, and control, you need those. All right, more vocabulary. Confounding is when levels of one factor are associated with the level of another factor, so their effects cannot be separated. Lurking variable is a variable that has an important effect on the relationship among the variables, but is not included in the study or experiment. And statistically significant is seeing an observed result or difference so often that it is most likely not due to chance, and instead is the true response in a study or experiment. All right, go Seahawks.